All right, so we are starting a new unit with this set of videos. We're going to be learning about forces. And our first video is going to be kind of a fun one because we're just going to learn some interesting things about the world around us. Some of you guys may already have touched on this or like watched a YouTube video here and there about this, um, but we're really talking about forces. And before I do anything else fancy with forces, I need you guys to realize that forces are actually very simple and easy to identify. A force is any pull or push. If an object is being pulled or pushed in any direction, each pull and each push acting on it is caused by a force. And that's all there is to it. If you can identify a push or identify a pull, there's a force. And if you can't, then there's no force there at all. It turns out that there's actually only 4 forces in the entire universe that we know of. There's other things that we call forces and will treat as forces, but they're really just big versions of these 4 fundamental forces that exist in the universe. The very first one is gravity. Gravity is a force that you would be very familiar with. It's been called at various times. My favorite name for it is spooky action at a distance. And it's called that because unlike the forces that were known for a very long time, or people thought they knew for a long time, it was this weird force that could act over huge distances. So if this is the very small Earth that I've drawn right there, then we know that like gravity can affect objects at distances farther and farther away from it. And even though it's to lesser and lesser extents, it still affects these things that it has no way of actually touching. And so here close to the Earth, we might have an acceleration due to gravity of 10 meters per second squared. And then a little bit further away, it might be 9 meters per second squared. A little bit further, it might be 8 meters per second squared. My scale here isn't really perfect, but it turns out that actually the International Space Station is about there. Actually, on the other side of that line, I think it's about here. It's at about 8.9 meters per second squared. There's actually quite a bit of gravity still there, even though we think of them as being way out in space. So this thing out here is called a gravitational field. And the reason why gravitational fields exist is only just starting to be understood by scientists. We're starting to detect things like gravitational waves and start being able to see gravitational events way off in space, which is letting us, if not do experiments, at least collect data that we've never been able to collect before. So it's an exciting time because gravity for a very long time has been a mystery to humans. We know what gravity does. We just don't know why gravity does it because it's just so hard for us to manipulate it. Gravity is actually an attraction between masses. And it's very weak compared to the other forces. The only reason it seems to be strong to us is we just happen to live close to something that has a lot of mass. But by comparison, some of our other forces, you can get much more force out of way fewer objects. The equation for the force of gravity, and we'll talk about this way more later on in this unit, is G m1 m2 over r squared. This is called the universal gravitational constant, and then it's based off of the mass of the 2 objects involved and the distance between them. And another formula for it looks like this, that's related to it, that says the gravitational field is based off of the force of gravity on an object divided by the mass of that object. So we'll be dealing a lot more with these, the idea of gravity a little bit later in this unit, but it's one of the first fundamental forces that we ever recognized as humans. And while we know that it affects everything from planets to why our feet stay on the ground, and even is important for like various parts of human circulation, a lot of it's currently a mystery. The next force is actually much more understood. And this is called the electrostatic force. So the electrostatic force is it's the attraction between charged particles. I spelled that wrong. Attraction between charged. And this electrostatic force is actually the source of every other force that we're actually going to deal with this school year. Those of you guys who took chemistry or are familiar with chemistry, we know that we have these things called nuclei, and each nuclei has a positive charge. Because they're filled with protons. And then there's little charged particles called electrons that kind of fly around outside. And there's an attraction between electrons and the nuclei that not only keeps the electrons close to the nearest atom, but also tends to form these things we call chemical bonds, which are really just attractions between electrons and different nuclei. And that attraction of the positives and negatives pulling together is what causes everything that exists in our universe that we can interact with. Are these electrostatic forces interacting. So if you think about pushing down on the table, what you're really doing is you're pushing on it, trying to force those atoms apart. And the reason why you feel that desk push back on you is because those molecules are trying to stay together, and they, similar to like if you pushed down on a spring and it would push back, they're going down until they refuse to go any further, and then they're trying to push back, trying to get back to their original shape. The electrostatic force even explains why when you touch a table, your hand doesn't go through the table. And that's because the electrons on the surface of your hand and the electrons on the surface of the table push against each other. So you don't actually even touch the table. You're repelled before your electrons or anything ever actually interacts. So if you're thinking to yourself, does that mean that I've never and will never actually touch another human? It does mean that. You will never really know another person because you can't physically touch. I'm sorry. But if it makes you feel any better, you are mostly empty inside. So that's the good news about the electrostatic force. And the formula for electrostatic force is again something we'll get to later on in the school year, or the semester, I guess. It is KQ1 Q2 over R squared. This is called Coulomb's constant. And then we have the charge of each object divided by the distance between them. If you notice that that formula happens to look very similar to the formula for the attraction due to gravity, you're not the first one to notice that. And this bugs scientists like a lot, that these two formulas seem so similar, but they've struggled very hard to find like some kind of concrete reason for it. And there's some models that have like attempted to it, but nothing that's been proven. That's proven why like gravity and electrostatic force should seem so similar. So gravity and electrostatic force. I just want to mention anything that you see that involves a push or pull, where it's physical objects, contact forces, is really just a macroscopic version of electrostatic forces. It's either that object trying to avoid being pulled apart, so it's pulling back on you to stay together, or it's trying to avoid being broken by having your hand or something push through it and holding together and pushing back against you when you try to do that. All right, we still have two more forces to get to. Oops, that's not a good slide. Hold on, okay. There's a good slide. And we have the last two. We have strong nuclear force. And strong nuclear force is a fun one because maybe this has occurred to you if we were just talking about electrostatic force. Electrostatic force is an attraction and repulsion. I don't think I said that. Oops. Attraction and repulsion between either like particles or unlike particles. Like particles repel, and the core of every atom is made out of protons that inherently are positive and are constantly repelling. So it always bugged me when I was going through chemistry that the nucleus of atoms would not just explode. And for whatever reason, when I took high school chemistry, that was not explained. The reason why was not explained to me. The reason is strong nuclear force. This is specifically an attraction between nucleons. It's an attractive force between neutrons and neutrons, protons and protons, and neutrons and protons. Anything that exists within the nucleus of an atom is attracted by this strong nuclear force. Strong nuclear force is stronger than the electrostatic force, but it acts over much smaller distances. So there's a constant tug of war in the core of an atom between the force of repulsion of all of those protons and the strong nuclear force pulling everything together. And radioactive particles come from this. If we end up having too much electrostatic repulsion and not enough strong nuclear force attracting, then eventually that atom's going to fly apart and it can't stay together anymore. So that's the strong nuclear force. It's cool, so I wanted to talk about it, but it actually doesn't come up at all this school year, other than just kind of like knowing that it's there, knowing that it exists. Our last force is even weirder. This is the weak nuclear force. And weak nuclear force governs, okay, this is going to be so weak, my explanation that is, governs neutron decay. And by that I mean something about weak nuclear force makes neutrons decay into protons and electrons. And that's all I can really say about that. I've tried learning more about weak nuclear force, but it doesn't really fit into this whole idea of attraction and repulsion, it seems, the way the other three fundamental forces are. There's some more going on there, and I'll be honest, I don't have the background in nuclear physics to really go any further into weak nuclear force. The good news is you'll never, ever be asked any questions in AP Physics 1 or AP Physics 2 about weak nuclear force. So if you want to learn more about it, please feel free. And if you learn some cool facts about it, share it with me, because it's definitely an area that I don't know everything, or I don't know much at all. So those are the four fundamental forces, though. Gravity, which is going to be pretty much in every problem we deal with this school year. Electrostatic force, which is going to show up at a macro scale, this entire unit, even though we're not going to deal with it specifically between particles. And then these other two that are just only going to be handled very lightly. So now that we know the four fundamental forces, we're going to start looking at some of the ways to identify forces in our next video. So, excuse me. Thanks for watching.